So I'll repeat this again. So my name is Nikita Ivanov. I'm a founder of a company called GridGain Systems. I'm also on an Apache PMC for Apache Ignite. So what I'm going to talk about in the next about 40 minutes, and we're probably going to leave about 10 minutes for Q&A. So if you have any questions, let's just wait till the end. We'll talk about some of the ideas of Apache 2.0. I was actually pointed by a few folks here that, just not to be confused, Apache 2.0 is not a release yet. It's just basically an idea of a roadmap. So we as a community are thinking what we should be working on Apache Ignite towards 2.0 release, which probably will happen somewhere towards the end of this year, maybe later. But we basically started thinking about some of the ideas, what we want to see in Apache 2.0 going forward. And that's the presentation to give you some of the hints, some of the ideas, some of the basic conversation we're starting to have in the community around Apache Ignite. So that's the quick agenda we're going to be talking about. Let me skip right over here. So, by the way, Apache Ignite is Apache Ignite, it's Apache project. Join us. This is the awesome community. It's one of the most interesting projects in the Apache Foundation. We very welcoming community right there. You can start very easily. We have plenty of interesting tasks. So anybody wants to join Apache, look at Apache Ignite. We always welcome the contributors. There's plenty of tasks of very different levels, from simple to complex. You can always pick what you like. Please join us. There's a couple of links over here, but basically just Google Apache Ignite, go to the website, you'll find your way out. It's very, very simple. So the theme of this presentation, or essentially the whole idea about Apache Ignite 2.0 roadmap, is to talk about the convergent data platform. It's a pretty loaded term. It's a pretty marketish term. But we'll get to it, and I hope I'll give you some of the in non-marketing and more technical understanding of why the convergent data platform is really a key idea for us to move forward as a community of the project. But let's talk about the fast data versus big data. This is two terms. Again, it's a very marketish, and we're gonna kind of unwrap them pretty quickly. So why are we talking about the fast data and big data? And that's basically, this slide gives you a pretty good kind of high-level overview. Let's start with the fast data. I'm sure you heard it. And unless you kind of know marketing, product management, you don't really know exactly what it means. So typically, fast data really talks about OLTP, our traditional online transactional processing. So basically, it's a small operational data sets, very important high throughput apps per second, low latencies, and probably the most important part was it's all about consistency in being transactional. You know, if you look at the OLTP definition from many years, if not decades ago, it's all about consistency in transactionality as well as the high ops per second, high throughput things. Compared with the big data, something we've had literally for the last maybe a decade, if not less. It's predominantly OLAP, it's analytical processing, as we know it from history. But it's all, the difference here, unlike the, fast data really deals with the small data sets. Our big data definitely deals with large historical data sets. It's a larger historical data sets. It's predominantly read-mostly. And I would say it's not predominantly, it's almost always read-mostly data. We don't really update historical data sets. Throughput is not important, surprisingly. Still, the low latency is important, but throughput is not really important because we don't bombard our big data systems with thousands, if not millions, concurrent users. It's not happening. It's typically very different use cases. So, and performance typically good enough for interactive analytics. So this is a very important slide because it gives you a kind of differences, right, between traditional fast data and the big data. So once again, the fast data, small data sets, extremely important high throughput, and low latencies. And obviously, data is updatable. It's write-read data. In the big data world, again, we talk about predominantly large data sets, very large data sets. That's where petabytes really come to picture. We're talking about the predominantly read-only data sets, and throughput is not really important, although latency is obviously important always. So some of the ecosystem of the fast and big data. On the fast data, we have essentially quite a few projects, as a matter of fact. On the streaming side, we have Flink, Kafka, and Apex. I think all of them from Apache. We have memory data grids. We'll talk about them, what they do. Things like Ignite, Hazelcast, GOut. In memory databases, things like MemSQL, VolDB. Well, again, we'll talk a little bit more details what they do and what they do not. And obviously a variety of hundreds of NoSQL databases, things like Mongo, Cassandra, Couch, and list goes on and on and on. On the big data side of things, surprisingly, the ecosystem is not as large, but it really represented by very large projects. Naturally, Hadoop and everything that coalesce around the Hadoop, things like the MapReduce, HDFS, and HBase, and 20 other things. In the last couple of years, Spark obviously is a common replacement for MapReduce. So anything to do with machine learning, graph processing, slow SQL, Spark is the deal there. And we have, on the commercial side, we have still quite a few commercial warehouse and DB vendors on this space as well. Things like potentially Netezza, Teradata, and things of that nature. So it's a fairly kind of loaded ecosystem, right, on both sides. I think if you count extensively, you can find probably about 100 projects on each side. This is the kind of more known ones. But nonetheless, the ecosystem is pretty large. So let's talk about the fast data memory databases, because we get these questions a lot, as well as on the Apache Ignite community, as well as the GridGain as a company behind it. So what is the deal between in-memory databases and traditional in-memory data grids? That's the question we get asked very frequently. And that's it's a good slide to overall understand what do in-memory databases do in this context. So typically, when we talk about in-memory databases, we talk about the two specific databases, MemSQL, VoltDB, both great projects. MemSQL actually closed source, but has a free community limited edition. VoltDB has recently been open source, and just have an enterprise version of that as well. So the traditional databases essentially use disk for storage. In memory systems, in memory databases, use memory storage. That's it. It's very simple, rather trivial, right? So in memory databases, use RAM across multiple computers potentially as the main data storage. So they share a lot of the same characteristics as traditional databases. It's a high throughput, the low latency environment, obviously. What's really unique about in-memory databases, they're a database, they're RDBMS, so they have a full, unabridged, unlimited SQL support. So if you look at the MemSQL and VoltDB, if you really want to have the easiest migration from SQL to SQL, that's your solution, because migration is typically very trivial. It's basically full SQL support. Now, this is also an Achilles heel of this product, because SQL is the only API they support. And if you look back 20, 30 years ago, that was fine, because 20, 30 years ago, all the back-end processing was SQL-driven, right? And having SQL only would be enough. Today, that's almost factually false. Today, the world is way beyond just a SQL, right? We have streaming, we have kind of MPP processing for a large parallelized computational job. We have all kinds of different types of processing, like a key value and data grades. And SQL really is just one option that you have when you're dealing with the data processing in the back end. So I do believe that's one of the most significant Achilles heels for in-memory databases, because predominantly you're still stuck with a SQL-only view on the world. And 2016 and going forward, that's just simply not enough. But these projects essentially are great in what they do. If you guys absolutely sure that that SQL is the only thing you need to have when it comes to fast data processing, then these two projects and quite a few others are an excellent addition on this. And as I mentioned to you, probably one of the biggest advantage of that, again, it's ease of migration. You can literally grab MemSQL and replace your MySQL very easily with it. So data grids. Data grids is a little bit different beast. There's probably about a dozen of different projects and products that we can mention. You can find in this conference, naturally, quite a few of them. Ignite and GridGain is here. Friends in Hazelcast is here. There's quite a few other projects here. GR, I'm not sure it's here in this conference, but I'm sure somebody from this project is well available here. So there's quite a few projects and products, open source projects and commercial products in this area. So data grids actually share some of the high level characteristics with databases. They're still about high throughput and low latencies. There's no difference here. But fundamentally, that's where the similarities really end, because most of data grids really based on a key value store. And that's a very important point. The key value store, the whole kind of, a hash map-based representation, if you will, of data, is very important because it's fundamentally the basic and most kind of, moldable data structure you can keep the data in. Because once you have data in a key value store, you can really view this data in very different ways. You can view this data as a SQL store. You can view this key value store as a file system. You can view it basically for a MapReduce or MPP type of processing. You can basically view this data in any different way. And that's what gives this tremendous flexibility to data grades. Like, for example, in Ignite, we already today support a SQL, almost full SQL 99 capability. We support multiple MapReduces type of processing, right? One is Hadoop compatible, one is in our own. We support file system view on the same data. We support streaming. We support classic HPC parallel programming, all on exactly the same data set. As a matter of fact, you can basically store a file through a file system and query the same file through a SQL interface. That's a unique capability, not only about our project, but it's a unique capability of this fundamental idea of storing data as a key value store and then basically give you all the different type of views on that data. Naturally, you have a key value, by the way, as well. But then you have all the different things as well. Transactions. This is the one area where, again, in-memory data grids are similar to the in-memory databases. As a matter of fact, not all data grids support transactions. And I'll be biased here to say that only the best ones support. But transactions are pretty important, obviously. We've learned, I think, this here in the Silicon Valley, we kind of, modulating between, our ideas. And, if anybody remember 5-7 years ago, classical transactions was a banned word, and it was bad, bad, bad. Nobody needs it, nobody wants it, right? 5 years passed, we were all kind of, chalked on eventually consistency, and now we kind of understand, hey, yeah, for 80% of the cases, we don't need to have them, but for those 20%, we gotta have a normal transactions, and it's impossible to emulate them with eventual consistency. So that's why, we kind of, swung back into the idea that we need to have normal transactions. And we also need to have eventually consistent transactions for the cases when we don't have to have strong consistency and want to get back to performance. So in Ignite, for example, we have a very interesting idea. And that's, when I speak about Ignite specifically, I'll talk about this a lot. But very quickly, in Ignite, we decided to go a very different route when it comes to transactions. Unlike anybody else in a kind of NoSQL space generally, we decided to implement first a classic two-phase commit protocol first and really optimize it to no end. And then basically gives you the option to relax some of the consistencies within two-phase commit protocol to gain back performance when you don't need the consistency but prefer the performance. So in this model, you still have, by default, all the capabilities of a traditional two-phase commit transactions, exactly the same transactions you have in your typical Oracle installation, pessimistic, optimistic, all installation levels. But then, if you don't need to have consistency, you want to get back to performance, you can still relax some of the consistency, for example, like make the commit messages asynchronous, and get back almost the same performance benefits you would get from a traditional, eventually consistent caches or transactions. Yet, you still have normal transactions available to you. This is one of the greatest things about Ignite, that it doesn't really force you to basically some kind of monkey dancing with the transactions when it comes to eventual consistency. You do have normal transactions, and you can fall back to relaxed consistency when you don't have to have them. It's a very nice idea versus basically having only relaxed transactions and have no other way to move all the way to a fully consistent transactional behavior. So typically, data grids have extensive data querying capabilities. That basically goes without saying. Remember I told you about the key value store and how many different views we can give it to you, right? So we have SQL, we have key value access, we have predicate scanning, you have plenty of things depending on the project. In Apache Ignite, we have all of them. And typically, what's actually very surprising for anybody new coming to in-memory processing, all the in-memory computing projects have extensive disk storage. I always keep talking about it, talking about in-memory projects as memory first, disk second. It's never memory only, just the same way as normal databases is never disk only, right? Think about this. If you take a typical database like Oracle, it's predominantly storing data on the disk but has substantial in-memory caching, right? For the data that's, every database would have caching for the last 50 years. In-memory systems, just reversed. They use memory across multiple computers as a primary data storage, but they also use disk extensively for for durability and for spill overflow and so on and so forth. So that's a basically kind of big high level, I would say, high level overview of data grids. Let's talk about a big data ecosystem. I'm going to spend too much time. You guys know pretty much all of it. It's a big family of products. It's predominantly about batch processing, read-only data. There's some in-memory processing in Spark. Spark is a great project as an example of what you can do in memory. Some of the main features, it's predominantly disk-based. Even up until recently, even for Spark, if you want to store the context between Spark jobs, you have to drop them somewhere. And typically, we drop into HDFS to something like Tachyon or a strong file system. So even for Spark, anything beyond the context of a single job execution was a disk-based system. So it's changing, thanks to the Apache Ignite, but nonetheless. It's predominantly all about interactive analytics. I know it's probably inobvious for you, but believe me, I remember talking about this subject 3 or 4 years ago. There was a lot of confusion in that people didn't understand that Hadoop and Hadoop-related projects were never designed for any real time. It's not that engineers were bad. It's completely wrong. Engineers were pretty brilliant who worked in Hadoop, but the system was designed for interactive usage, meaning that somebody types a command, can wait 5, 10, 20 seconds, sometimes hours, and get results back. That was the use case for Hadoop and Hadoop-related projects. It was never designed for anything to do within a few seconds, let alone milliseconds or microseconds. So Spark in exactly the same territory. Spark is not a real-time system. As a matter of fact, our SQL execution, give you an example, our SQL processing on Apache Ignite is about 100 times faster than Spark. Again, not because we're smarter, because we optimize for real-time processing, including the SQL, and Spark is not. It was never designed for it. It was never intended to do so. So all the systems here, including Spark and Hadoop, are predominantly for interactive analytics, basically meaning it's a speed of a user. You basically can type something and wait for something and get results back. No transactions. Kind of goes pretty obvious, but nonetheless, when you're dealing with analytical data processing, you don't really need transactions. You don't transact on analytics because there's no updates, right? And when you read, you don't have to have transactions, as a matter of fact. So most, if not all, big data projects have no transactions. Again, they don't need them, but that's a fairly significant disadvantage. Because of read-only data sets, it's probably can reverse that. Read-only data sets read the idea of no transactions. But they all have strong querying capabilities. That goes without saying. If you look combine HBase, combine Hadoop with its strong MapReduce, with the big and Hive and all the things around this, if you combine Spark, the big data ecosystem has a very, very strong querying capabilities. Has a relatively low latencies for a single Spark job execution that's pretty fast. But again, even forget about throughput. Even low latency is not really a big strength of this. Of big data. So all this kind of generic talk, I specifically want to basically talk about all of this so that we can basically start to think about what is the Convergent data platform, why we're at the Ignite community pretty excited about this idea. So how do we bridge the gap, right? So the whole idea of a convergence, it converges between OLAP and LTP, convergence between fast data and the big data, if you will. So can we create a project, or can we extend the project like Ignite to really cover the both ends? And so essentially in the fast data, you really need to add a disk-based processing. Because on the fast data, you remember that one of the biggest disadvantage, it really deals with the smaller data sets, right? And typically memory systems don't really span beyond tens of terabytes. We work with some of the big clients in the world, and we've seen terabytes. We never even talk about petabytes. So the in-memory systems today are anywhere from 0 up to a teens of terabytes. And obviously, the big data systems are starting there. Nobody's using Hadoop for gigabytes, right? It's always the bigger data sets, and for larger companies, it could be really in petabytes and whatnot. So one of the deficiencies on the fast data is to really add a disk-based storage, so we can somehow store and process a bigger data sets that would naturally not fit in the RAM today. On the big data side of things, definitely add transactions and transaction capabilities. So add, read-write data sets, something that, things like Hadoop, for example, and Spark don't really do well at all. You cannot really update as much in Hadoop, for example. It's defaced as the read-only system, or append-only, if you will. So some ability to actually have a shared memory store or add read-write data sets or add transactions to the big data would be nice. So if we can do to both, obviously, somehow, it's not going to be as clean as pretty as this picture, but somehow, if we want to bridge the gap between the two, we need to add the disk-based storage for memory systems, and we need to add some transactionality and read-write capabilities for big data sets. So, and that's exactly what I just described. So the Convergent Data Platform, by the way, there's plenty of names for it. If you talk to Gartner folks, it's going to be HTAP, which stands for a hybrid transactional analytical processing. If you talk to, I think, Forrester, it's translytic processing, which is the combination of transactional analytical processing. I think the Convergent Data Platform came from 451 Group report. I think that's, we kind of heard it, pretty big way. So there's multiple different names from that, from analysts and from kind of community, but we kind of like the Convergent Data Platform as an idea. So it's a fast data plus big data. Again, it's a very loaded term. Again, I don't want to sound like too marketing-ish in this presentation, but somehow combine capabilities of the fast data processing, in-memory, transactional fast, with some capabilities of big data processing, which is the large data sets. So some of the interesting ideas about HTAP, as I mentioned to you, is fast data in memory, big data in disk. Think about this. Wouldn't you like to have a single system, a single project that can handle the fast data by keeping this data processing on memory? It can also handle the big data sets by keeping them partially or fully on disk. Wouldn't it be nice to have exactly unique, same, I wouldn't say unique, but consistent API to this entire data set, where a portion of that can be on RAM, portion can be on disk, and the system can take care about most of it. Surprisingly, for this very trivial, simple idea, there's not a single project today that does that effectively. Think about this. It's a very obvious idea, right? Most of you right now thinking that this is like, so what? Surprisingly to this, there's not a single project today, not a single one, that does it in any significant way. So you can think about, cache for database, but again, you don't really control cache in database. You can really do anything. It's completely hidden from you. You cannot really control how much in the cache and what's in cache and what's not. Even in Oracle, you can ping a table to the RAM, but that's about the extent that you can do. In data grids today, it's the reverse situation. We do everything in RAM, but we have very little kind of control what goes to the disk. We cannot really move the data to the disk and query it in the same way. So although many, many projects do store data in both places, none of them provide a consistent, simple API to query and process data across multiple data storage layers. It's a very interesting situation where we kind of all obviously understand the problem, sort of obviously understand the solution to that, and yet not a single project yet has gone into this. So we do believe that in Apache Ignite, as the next version comes around, something like 2.0, this is the area where we try to drive to. So let me talk about some of the couple ideas about Apache Ignite. How many of you guys, can you raise your hand, how many of you guys actually know about anything about Apache Ignite? All right, so about half. So I'll be very quick because we have little time left. So Apache Ignite is a really in-memory data fabric. Think about this. It's a type of software that allows you to move data away from disk and flash into the RAM across multiple computers. And from this point on, things will go dramatically faster. That's a simple idea. Once we move data into the RAM, we'll give you all different types of processing. In SQL and MapReduce and the key value in the file system, all kind of different, and streaming, by the way, all kind of different processing of this data in RAM. And really, the whole idea with memory data fabric is speed and scalability. We'll get the speed by moving data into RAM, and RAM is about 1 million times faster than any disk or any flash device. And we'll give you scalability because in-memory system typically scale across many, many computers to really gain the capacity in RAM. So we'll give you this in a classic parallelization of processing, and we'll give you the speed by running everything at the speed of RAM, which is dramatically faster. So architecturally, typically slides in between your data sources right there on the bottom and your applications on top. So if you have your data source like SQL, like HDFS, your NoSQL databases, straight up file systems, we can basically be right on top of that, and between your apps talk to us, and again, there's all the speed and scalability characteristics we talked about. So this is some of the key components we have on Ignite in Memory Data Fabric. We're not going to go through them. We're going to concentrate on data grids today. But just to give you an idea of what we call a cell fabric, it's not a single trick pony. We have data grids, we have a compute grid, we have service grid, we have a streaming grid, we have a Hadoop and Spark acceleration integrations, we have file system in memory file system, we have messaging events and data structures and plenty of other features. So this is one of the idea about originally from Apache Ignite project. I can remember I wrote with Dimitri Setrakan. We wrote the first line of code about 10 years ago for this project. So it's a very mature code base. We have thousands of deployments. An idea, surprisingly, idea from a day one, I clearly remember that, from a really first, commits to the project was, can we kind of move away from just being in-memory cache? Can we actually open up in other use cases, like compute grid, like data grid eventually, like streaming in memory, like in the messaging, like service grid in memory. So because we've seen a lot of feedback from our early customers that basically saying, look, just the key value is not enough. Our use case is more complex. Can you guys do the same thing you have in RAM, but with the different APIs? That's how the idea about the fabric came around, is that you move data into the RAM across multiple computers, and then we give you all the complexity and sophistication of different type of processing of this data. Because not a single project is a look-alike. Sometimes you need SQL, sometimes you need MPP processing, sometimes it's just the compute processing like Monte Carlo. Every project is different, yet it can be run on Ignite very effectively. Let me give you one example of this use case. I think Dimitri either talked about it already or will be talking tomorrow about this use case more extensively. But we work with Sberbank, one of the largest banks in Eastern Europe, and they actually are moving the entire banking infrastructure away from Oracle and Oracle-based products onto Ignite entirely. We talk about everything, back office, investment, risk, anything you like. So basically, it's a very massive undertaking. It's a bank size of Barclays. It's a very large global bank. I think they have about 200 million customers across Russia, in Europe, and Eastern Europe. And we basically, just a bit of advertisement for Apache Ignite, for GridGain itself. They basically wanted to migrate to a in-memory data grid architecture, minimize dependency on Oracle. Definitely open source played a huge role in this decision. And over the long POCs, we kind of won this deal. And we demonstrated one of the best performance. And one of the key things for them were a fault tolerant scalability. And this kind of goes without much saying, but again, in memory systems, that's a big deal. When you keep stuff in RAM, the tolerance, the fault tolerance, and eventual scalability matters a lot. SQL 99, access, transactional consistency, those are key features we kind of won this deal on. But again, this kind of shows you that in memory computing, if it's done right, and if it's really kind of a fabric approach to this, kind of more a strategic approach to memory, not just a single kind of single use case. It can be used in a very large projects. You can win pretty big deals. You can base your large organization business on this technology. And again, this is the one we work with Barclays, we work with Citi, we work with quite a few other large financial organizations, anywhere from mobile games backend, ad tech, and the list goes on and on. So we have all those different type of customers. Predominantly, what I'm trying to say is that in memory, if it's done right, is used today in a very interesting way. Companies like WhatsApp, Workday, predominantly in-memory based, and those are pretty good examples as well too. So let me talk about the Ignite data grid, because remember, data grid was one of the key components on the fast data things. Remember, the fast data is predominantly in-memory databases and data grid, and the big data is predominantly what we know about Hadoop and Spark, things of that nature. So data grid is a very important key component in a fast data stack. So in Apache Ignite, data grid is based on JCache API, by the way. So I think Greg Luck is here. He's going to be first. Soon enough, there's going to be a new version of that. We're going to be supporting this for sure. If anybody unfamiliar with JCache, I highly advise to look at it. It's a great API, and most of the major vendors support that. It's a standard API for local caching. So actually, data grid is based on the in-memory key value store. As I told you before, in-memory key value is a very important idea. Basically, everything else we do stems from this fact that we're based on key value store. So we support basic cache operation. We have concurrent map APIs. We have a collocated processing, which is the very important concept, is when you store data in distributed fashion, you have to have ability to collocate your processing with the data. Because if you don't collocate, you end up with a lot of noisy traffic. So the fundamental idea of any distributed processing, if you partition the data, you have to partition your computations the same way. Otherwise, computation will go to a different node that doesn't have a data. It will have to fetch the data that will kill your system right away. So almost any serious in-memory computing product will support that. We'll support it in a wonderful way. Another interesting idea is that we support fully ACID transactions. I've already mentioned to you how important it is. I can tell you straight away we have the best implementation of transaction capabilities on the market today. We won so many deals in so many projects just because of that particular feature. We have the best implementation of transactions, most performant and most complete. Again, we have both optimistic and pessimistic transactions. We have all isolation levels like you would expect from Java environment, read committed, read not committed, even serializable if you like it. We're all based on the proper version implementation of transactions and whatnot. We have SQL capabilities. We pretty close SQL 99, especially when it comes to data, the querying capabilities of that. What's interesting is about the use of a heap. We have in-memory indices, and we both can keep an on-heap and off-heap. And we also have off-heap completely available to you. One of the problems for all of us in the Java community is, right, that when Sun developed Java, there was no problem with the garbage collection in on-heap storage, right? And today, on-heap really chocks anywhere between 10 and 20 gigabytes. You cannot really have more on-heap storage than about 15 gigabytes if you're completely not optimizing. And it's basically one of the biggest problems in the Java community right now, because typical boxes today will come with 32 gigabyte of RAM and 64 gigabyte of RAM and whatnot. What do you do, right? So, well, most of us in this community, and Ignite is not an exception, we have very advanced off-heap memory capability. Essentially, the bottom line, we allow you to use the entire physical RAM on the box. We've just recently been tested on the Fujitsu M10 boxes. If you don't know what the Fujitsu M10 is, one of the first computers they can basically configure with 64 terabyte of RAM on a single box. Now think about this, 64 terabyte on a single Solaris box. Pretty amazing, especially if you kind of roll back 10 years ago, that was a data center. And today you basically get this, one rack size computer with 64 terabyte full addressable system. And by the way, we're going to be working with Fujitsu long, and after that, I'm going to be ensuring that Apache Ignite and GridGain works in the system, because it's one of the most amazing systems that exists today for that type of scale. So the off-heap is a pretty big deal, especially on systems like that. And we know we have automatic RDBMS integration. So remember I told you about integration with the disk, that every in-memory system is actually a disk-based system to a certain degree. So we have that as well for read-through and write-through behavior and whatnot. So very complex picture, but I basically wanted to highlight the difference between partition and replicated caching. It's two very important modes of operation. So don't try to understand this picture. It's a picture from my friend Dimitri, who is very proud of this. I barely understand what's happening here, but what's important here to understand that on the replicated cache, every node has exactly the same data set. And the partition cache is really partitioned. Data gets partitioned. Every node contains only one portion of the data that exists on, kind of partitioned for that particular node. It's a very important point. So in a replicated scenario, you have extreme high availability. Every node in the cluster contains exactly the same data set. On the partition side of things, we optimize for capacity. Naturally, in this case, you are limited by the size of a single node. On the partition cache, you're limited by the size of the entire cluster. What's really cool about Ignite is that we can mix and match those caches as much as you like. You can have hundreds of caches of replicated style and hundreds of caches with partition style, all in the same system, all configured differently, exactly for what you need, all managed the same way. I'm already getting the feedback that we have about 10 minutes left. So very, very quickly, this is basically slide-by SQL support. We have one of the most advanced, if not the most advanced SQL support across any data grades. And I say with a straight face. Not only we support full SQL 99, there's no gimmicks, there is no custom language, there's nothing. It's a straight SQL support we have. We have full support for parallelization for all the basic operations, group by aggregation, sorting. We have cross-cache joins, pretty good deal. We are about to release a non-collocated join, so basically you don't have to do a star schema for your joins to work effectively. Right now they would not work at all, like in most of the in-memory databases, in-memory data grids, you have to collocate and really use the star schema for your joins to work, because as you guys know, in SQL, joins can explode, and on large data sets you have to use star schema. We're just about to release a non-collocated ability for joins, so they will work always, you're just going to slow down. We have ad hoc SQL support, and something like VoltDB, where you have to know your queries up front. We don't have to. What's really cool, we also support a sort of the store procedures in a way. You can define any functions in Java, Scala, or anything language you like, in JVM language, and use that function right in a SQL query. It's a very powerful concept. That's essentially how you can define your own store procedures written in Java, or Scala, any other language, and use them directly in SQL, and they'll be executed properly. So this is basically an example of what we can do. It's a straight SQL. It's a very important point, by the way. A lot of folks keep saying about SQL, and when you start digging up, it's like fully bastardized, you know, some kind of subset of the language with the different keywords and whatnot. It's hard to migrate it, so you have to learn something new. For us, SQL. It's SQL 99, nothing to learn new. If you know SQL, you can know how to use it. This is a basic example of how you can run a pretty complex query. By the way, this is a join and the functions and whatnot. So you can run exactly the same queries you would. And by the way, we will absolutely parallelize it on the cluster. So we'll take care of all the parallelization, how to run this in parallel, how to get it all back, and everything else. You just give us this SQL, we run it in the most effective way. So I only have a couple of minutes, so I'll be pretty quick here. Part of the Ignite, what we do, remember that we talked about supporting the big data. That's what we do in the big data already today as part of a Convergent data platform story. We already support what we call a shared RDD across Spark jobs. So if you have multiple Spark jobs going, you can basically store results in a shared RDD. It's a very cool idea for Spark. It's a very popular addition to the Spark. You don't have to drop your results back on some file system and really kill the performance. You can keep your data from one Spark job to another right there in the RAM, get all the performance benefit of a Spark in memory, and not lose them because you have to use some kind of disk-based storage. So anybody who's using Spark, I highly advise to look at this and start using it. It's a part of Apache, it's free, and it's an awesome addition for Spark, something that Spark really misses. Spark is not data storage system. Keep this in mind. Spark is a processing framework. Has no idea how to store data, period. It's a processing framework. So this allows you to have an excellent storage layer for Spark. Highly recommend. In-memory file system. Nothing to do with Spark, but nonetheless can be used with Spark as well, but it's actually a bona fide file system. It's HDFS compliant. You can actually replace HDFS with this file system, or you don't have to. You can use it as a normal file system. Open file, write something to it, close it, delete it, whatever you like. It's a normal file system right in your memory cluster. It's an awesome thing. There's so many different use cases. Some of the operations, think about this, some of the operations are almost 2,000 times faster than the same operation in HDFS. Think about this, almost 3 orders of magnitude performance increase just by switching to this, which is the full HDFS compliant file system. MapReduce, in-memory MapReduce. So a long story, but we have a in-memory MapReduce implementation that's fully compatible with Hadoop, and that gives you a significant boost. Konstantin Budnik, run the demo multiple times for us, and he got about, 7 to maybe 8 times faster on exactly the same code base from Hadoop. Huh? 30, even better. So no recompilation, no code change, no nothing. Just basically download this Apache Ignite, install along the lines, and you get essentially anywhere between 7 to 30 times faster on exactly the same code base. Think about this, no recompilation, no nothing required. So the last slide on the slide. So I want to come, we talked about a lot of different things, right? We talked about some of the high-level things like fast data and big data. We talked about some of the ideas behind the Convergent data platform. So what are we trying to do in the 2.0 Ignite? Again, this is just a roadmap idea, so what we started to discuss in Apache dev list. So definitely want to get more SQL, and that's our drive towards supporting more of a, I would say more of a kind of fast data processing. So no collocated joins, we're going to be driving towards supporting full SQL 99 with full DML and DDL subsets, so we can define structures, we can define tables and whatnot. Also, we pretty much almost like 99% as far as the data modification language, but we'll get there as well. The biggest drive for us is to what we call advanced tiered model or tiered memory model. This is basically where we're going to erase any difference from API standpoint between memory, non-flash, whether it's SSD or any other flash devices, and traditional hard drives or network-attached storage. So we're going to create in exactly the same layer that we can store data in, and you can query this data or process data completely transparently, whether you store it in RAM, in flash, on disk, or network-attached storage. So as a matter of fact, from an API standpoint, you're going to be able to issue the same SQL query, the same key-value predicate, same MapReduce job, and it's going to work across the entire data set that can span petabytes. The only caveat, the more you have in RAM, the faster it will work. The less you have in RAM, the slower it will work. But you don't have to anymore, at least that's our idea going forward, you don't have to anymore think differently when I'm talking about a disk, flash, or RAM. You basically have one universal layer that consists both of RAM, flash, storage, slow, spinning rust, and network attached. And we can basically, it's going to be completely transparently for you. You can basically just issue the query, store data, work with it. And that's our idea, what we call Convergent Data Platform. And hopefully you guys are going to see it from Apache Ignite in probably less than a year from now. So I think that's my last slide. So if you have any questions, I'm more than happy to answer. You can append and drop? Trunk. Okay, I got it. So it is append and drop and append and trunk file system. Any other questions? And by the way, you don't have to ask them right now. We're there in a GridGain booth. Anybody welcome, and somebody from our company will be able to be there. All right. Thanks a lot, guys.